Neptune, the eighth and farthest planet from the Sun, orbits the Sun every 165 years. It has 14 moons, which are named after nymphs from Greek mythology, and is battered by supersonic winds. Despite its intriguing features, Neptune has only been photographed from close range by a spacecraft once. The Voyager 2 spacecraft provided humanity with its first and only close encounter with the planet nearly 33 years ago. Neptune, the third largest planet in the solar system after Jupiter and Saturn, hardly appears in our solar system's family photo albums. This is despite the fact that Triton, Neptune's largest moon, is virtually covered by a liquid ocean. In 1989, NASA's Voyager 2 passed close enough to Neptune to reveal stunning images that astounded scientists. The Hubble Space Telescope also contributed to our understanding of Neptune's features. Scientists eagerly analyzed these first true photos, and their discoveries continue to shape our understanding of the planet. Neptune, named after the Roman god of the sea, is a beautiful blue sphere. Pluto once held the distinction of being the farthest planet from the Sun, but it was reclassified by the International Astronomical Union. Neptune, which is over 3 billion miles away from the Sun, orbits once every 165 years, meaning it has not completed a full cycle around the Sun since its discovery. Known as a gas giant, Neptune is one of the 4 planets beyond the asteroid belt that fall under this category, alongside Jupiter, Saturn, and Uranus. These planets have no solid surfaces and consist of vast atmospheres containing hydrogen, helium, and trace gases. Neptune is the smallest of the gas giants, with an equatorial diameter of 3,775 miles, though it could house roughly 60 Earths in terms of volume. Neptune is so faint that it can only be observed through a telescope, with an apparent magnitude of 7.8, equivalent to the faintest stars visible to the naked eye. This made it impossible to observe Neptune before the invention of telescopes. In recent years, Earth-based telescopic studies have revealed intriguing hints of dynamic cloud structures on Neptune, which have allowed scientists to estimate the planet's rotating wind speeds. Voyager 2's encounter in 1989 was the first close-up look at Neptune, passing nearly 3,000 miles above the planet's north pole and about 2,500 miles from Triton. This close flyby led to significant reevaluations of our understanding of the solar system's outer planets. One of the most noticeable features in Voyager images of Neptune is its blue color, caused by the abundance of methane in its atmosphere. Methane absorbs longer wavelengths of sunlight, leaving only the blue wavelengths to be reflected. Despite receiving only a third of the sunlight that reaches Jupiter, Neptune is a very dynamic planet. Similar to Jupiter's massive storms, Neptune has dark spots on its surface, with the largest one being large enough to contain the entire Earth. This storm, which was initially speculated to be a vortex, was captured by Voyager 2 and dubbed the Great Dark Spot. This storm is comparable in size to Jupiter's Great Red Spot, but is more changeable in size and shape. Additionally, Voyager captured images of bright, cirrus-type clouds on the southern and northeastern edges of the Great Dark Spot, which may resemble Earth's lenticular clouds found above mountains. Another feature, known as the Scooter, is a fast-moving, irregularly shaped cloud that orbits Neptune in about 16 hours, possibly a cloud plume rising between different cloud decks. Voyager scientists also observed a second region, D255, located south of the Great Dark Spot. The heat radiated by Neptune's atmosphere varies with latitude, being hotter at the equator, cooler in the middle latitudes, and warm again near the South Pole. Neptune's magnetic field is also remarkable, as it shares polarity with Jupiter and Saturn, but it is opposite to Earth's. Voyager 2 discovered auroras in Neptune's atmosphere, which are similar to the northern and southern lights on Earth. These auroras occur over large areas of Neptune, not just at the planet's poles, due to its unique magnetic field. The auroral output on Neptune is estimated at around 50 million watts, compared to 100 billion watts on Earth. Neptune's moon Triton is particularly interesting because it is the only large satellite that orbits Neptune in a retrograde motion. This suggests that Triton was likely captured by Neptune, rather than forming in its vicinity. Voyager 2's images of Triton revealed active geysers that shoot nitrogen gas and dark dust particles into space, indicating a fascinating geological history. Triton's high density and retrograde orbit support the theory that it was once an independent body before being captured by Neptune's gravity. Triton, with a diameter of 1,680 miles, is the coldest known place in the solar system, with temperatures around -235 degrees Celsius. Despite its extremely cold surface, water ice on Triton behaves more like rock due to the low temperatures. The surface of Triton is mostly made of water ice, and at temperatures of nearly -100 degrees Celsius, nitrogen and methane freeze into a solid form. These elements are responsible for the eruptions seen on Triton's surface. Images captured by Voyager show geyser-like volcanic vents, where nitrogen gas and small black particles are expelled into the atmosphere, some reaching altitudes of 1 to 5 miles before being blown by the wind. Voyager 2 also observed Neptune's rings, which had previously been hypothesized to exist. The spacecraft's images revealed that Neptune's rings extend all the way around the planet, although Earth-based telescopes had difficulty detecting them due to their diffuse nature. These rings are composed of fine particles, and Voyager's discoveries helped astronomers determine the number of rings and provide tentative names for them. The rings are shepherded by small moons, which help prevent the particles from either escaping into space or falling into Neptune's atmosphere. The surface of Neptune is covered by thick clouds, and its interior consists mostly of dense, pressurized gases, with rock and ice making up the majority of the planet's inner layers. Though much remains to be understood about Neptune and its satellites, the Voyager 2 mission provided invaluable data that has shaped current knowledge of this distant planet. The future prospects of Neptune and its moons remain a mystery, but ongoing research continues to uncover more about this fascinating world. Neptune's extreme distance from the Sun means it experiences some of the most inhospitable conditions in the solar system. As one of the most distant planets from Earth, it takes nearly 165 years to complete a single orbit around the Sun. Given its vast distance and the cold, dark environment it resides in, Neptune remains an elusive and enigmatic world, one that has only begun to reveal its mysteries in recent decades. Its environment, shaped by violent winds, high atmospheric pressures, and dynamic cloud formations, makes it an incredibly unique and captivating planet to study. Unlike the inner, rocky planets like Earth, Neptune is a gas giant, composed mostly of hydrogen and helium, with traces of water, methane, and ammonia. Its atmosphere is not only rich in methane, which gives the planet its characteristic blue color, but it also holds large amounts of hydrogen sulfide, which could potentially form clouds made of sulfuric acid. This atmosphere is far from stable, with incredibly strong winds and turbulent weather patterns that frequently reshape Neptune's features. At its highest wind speeds, Neptune experiences winds of up to 1,200 miles per hour, which are some of the fastest recorded in the solar system. These intense winds contribute to Neptune's ever-changing weather patterns, including massive storms and cloud structures that appear and disappear in short timescales. One of Neptune's most interesting features is its lack of a solid surface. Instead, the planet is surrounded by thick layers of gas and clouds. The lower layers of its atmosphere contain gases that transition into a more fluid state as pressure increases, forming a slushy mix of hydrogen, helium, and water. Deeper still, under the immense pressure, scientists believe Neptune may have a core composed of rock and metal, surrounded by a deep ocean of liquid water, methane, and ammonia. However, due to Neptune's remote location and the technical challenges involved in exploring such a distant world, much of its interior remains speculative. The planet's magnetic field is another fascinating aspect of Neptune. Unlike Earth's relatively symmetrical magnetic field, Neptune's magnetic field is tilted at an unusual angle of about 47 degrees to its axis of rotation. This means that the planet's magnetic poles do not align with its geographic poles, creating a highly dynamic and complex field. Voyager 2's data revealed that Neptune's magnetosphere is extremely turbulent, with chaotic magnetic field lines that likely play a role in the creation of auroras seen near the poles. These auroras, much like Earth's northern and southern lights, are caused by charged particles interacting with Neptune's magnetic field, resulting in beautiful light displays. Neptune's moon Triton, with its retrograde orbit and active geysers, continues to be a subject of intense scientific interest. It is the only large moon in the solar system that orbits its planet in the opposite direction of its planet's rotation, indicating that it was likely captured by Neptune's gravity long after the formation of the planet and its original moons. Triton's surface is covered in vast plains of nitrogen ice, and the moon's extremely thin atmosphere is composed mostly of nitrogen gas. The geyser activity on Triton suggests that the moon may have a subsurface ocean beneath its icy shell, where conditions may be suitable for the existence of life. The eruptions observed on Triton shoot out nitrogen gas and fine particles of dust, which creates geysers that shoot high into the sky, reaching altitudes of several kilometers. This activity has led scientists to speculate that Triton could have an active interior, potentially heated by tidal forces from its eccentric orbit. Although Triton is one of Neptune's most notable moons, it is not the only moon that captivates researchers. Other smaller moons orbit Neptune, each with their own unique characteristics. For example, Nereid, Neptune's third-largest moon, has an eccentric orbit that is unlike any other known moon in the solar system. Nereid's orbit takes it on a highly elongated path around Neptune, varying from as close as 1.35 million kilometers to as far as 9.66 million kilometers from the planet. This erratic orbit makes it difficult for scientists to determine the precise history of the moon's formation, but it likely has a fascinating geological and orbital history. Neptune's rings, though not as prominent as Saturn's, are another intriguing feature. Unlike Saturn's bright and easily visible rings, Neptune's rings are faint and hard to detect. The planet's rings consist of dark, dusty material, which gives them a relatively low reflectivity. They were first discovered in 1984 through observations from Earth-based telescopes, and Voyager 2 later confirmed their presence during its flyby in 1989. The rings are composed of small particles, which range in size from micrometers to a few meters in diameter, and their existence is likely the result of the gravitational interactions with Neptune's moons. The particles in the rings are thought to be made primarily of ice and rock debris, possibly from comets or moons that were shattered or captured by Neptune's gravity. The discovery of Neptune's rings and their composition has helped to deepen our understanding of planetary ring systems in the outer solar system. While Neptune's rings are not as spectacular as those of Saturn, they are still significant in their own right, and they provide valuable insights into the dynamics of small moon systems and the evolution of planetary rings. The existence of shepherd moons, small moons that orbit near the edges of rings, also helps to explain the structure and formation of Neptune's faint rings. These shepherd moons prevent the particles in the rings from spreading out into space or falling into Neptune's atmosphere, and their gravitational influence creates gaps and ring arcs. Understanding Neptune and its moons, including Triton, Nereid, and the other smaller satellites, is crucial for understanding the outer regions of our solar system. Neptune and its moons are often considered the least explored part of the solar system, and future missions are likely to focus on unlocking more secrets about this mysterious planet. The Voyager 2 mission, which provided humanity's first close-up images of Neptune, was a landmark in planetary exploration. However, as technology continues to advance, there are hopes for future spacecraft missions to revisit Neptune and its moons to answer questions about their origins, compositions, and potential for hosting life. In addition to missions to explore Neptune and Triton, scientists are also studying the planet's position and its role in the formation of the outer solar system. Some researchers believe that Neptune may have played a key role in shaping the orbits of objects in the Kuiper Belt, a region beyond Neptune that contains icy bodies, comets, and dwarf planets. Over time, Neptune's gravitational influence may have scattered these objects into their current orbits, contributing to the formation of the Kuiper Belt and helping to shape the architecture of the outer solar system. The study of Neptune also provides valuable insights into the formation of other exoplanets, or planets orbiting stars outside our solar system. Many exoplanets discovered in recent years share similarities with Neptune in terms of their size, composition, and atmospheric conditions. By studying Neptune, scientists are able to refine models of planetary formation and improve our understanding of how gas giants like Neptune form and evolve. The planet's atmosphere, with its extreme winds and turbulent weather, is also a key focus of research, as it offers clues about the behavior of atmospheres on distant planets that are too far away to study directly. As we continue to learn more about Neptune, we uncover the complexity of our solar system and gain a deeper understanding of the forces that shaped its creation. Whether it's the planet's mysterious blue tint, its violent winds, or its active moons like Triton, Neptune offers a wealth of fascinating features that continue to captivate scientists and space enthusiasts alike. Although Neptune remains a distant and enigmatic world, every new discovery brings us closer to understanding this fascinating planet on the edge of the solar system. Neptune's distance from the Sun also means it receives only a fraction of the energy that Earth does, resulting in a much colder environment. Despite this, the planet's dynamic atmosphere, driven by its powerful winds and internal heat source, leads to active weather systems. One of the more unusual aspects of Neptune is its heat emission. Despite being so far from the Sun, it radiates more heat than it receives. This suggests that Neptune has an internal heat source, possibly from the slow contraction of its core or from chemical reactions deep within the planet. Additionally, Neptune's orbit is not perfectly circular but slightly elliptical, causing subtle variations in its distance from the Sun. Over the course of its 165-year orbit, this causes Neptune's distance from the Sun to fluctuate slightly, impacting its seasons. However, Neptune's axial tilt is only about 28 degrees, similar to Earth's, which means it experiences seasons, although they are much longer due to the planet's long orbital period. Neptune's position at the edge of our solar system also makes it a key subject for astronomers studying the outermost regions of planetary systems. Understanding Neptune's composition and atmosphere not only enhances our knowledge of our solar system but also provides valuable insights into the processes governing distant exoplanets in other star systems.